Hello, everyone. Welcome to the Redshift and Tableau session. Today, we're going to be talking about the combination of those two products. My name is Adiascar Cisneros, and I'm hoping that's the most complicated thing you're going to hear from me today. It's actually my sister's name spelled backwards. But I'm going to tell you the whole story later, maybe at a bar over drinks. It takes too long. All right. I came to Tableau about a year ago, and I came from AWS. And before that, I was working at a company doing server migrations to clouds. So all in all, I've been working with AWS technology for about 10 years, and I've been certified for the last 5. Now, today, we're going to be covering a lot of material. So we need to have kind of a method to it. Now, the first thing I want to tell you is that all of this, the deck, all of these slides, and even references to deeper information about what I talk about is all included here, and you're going to get it after the conference. So don't worry about taking pictures, taking selfies, none of that. Close Facebook, please, for at least an hour. And I'm going to need you to focus on certain slides because we're going to look at concepts that are going to help us understand why we have recommendations for Redshift and Tableau. All right? So let's start with what we want out of this session. So the first thing that we're going to be looking for is understanding. I'm going to take you on a ride on my mind, because in order for me to understand a rule, I need to really, or accept a rule, I need to understand why that rule exists. So we're going to be kind of slowing down on understanding the technologies, and then we're going to be able to kind of breeze through the performance tips and recommendations. The next thing that I want you to get on board is what we're going to be referring to as performance. And yes, performance is an objective term. You start measuring from start to finish, and it gives a certain time. That's fine. But there's also another aspect of performance, which is what I'm going to call perceived performance. And I know it's a subjective term. But essentially, there are situations where you think you're getting low performance, and it turns out that it's just the way things are arranged that give you that impression. For example, recently, I was working with a customer, and they were working with creation of extracts, Tableau extracts. And their 5 extracts were not completing in a 5-hour window that they had designated. And we started working on all kinds of things because we got the impression that the creation of extracts was not working systematically, right? There's something wrong with Tableau server that's not creating extracts. And it took us what seemed like forever to change the order of the extracts, and it turns out that there were 4 extracts that completed in less than an hour each, and there was that long extract, except that it was first, at the beginning, it was executing first and not finishing in 5 hours, and that's why we were thinking that all extracts were broken, where it was just that one extract. And that completely changed our point of view and what we concentrated on. So I'm going to ask you to have an open mind when it comes to performance. And finally, we're going to look at how Tableau and Redshift interact with each other. But when it comes to performance, you have to have a systematic approach. And what I'm proposing today is we look at this as a river, as cleaning a river. If you go to the mouth of the river, the end of the river, and you start cleaning there, well, you're never going to finish because there's going to be garbage coming downstream. You have to start at the source, at the beginning of the river, and you start cleaning from there, and maybe when you get to the end, it's all clean, right? We're going to take kind of a similar approach. There's too many buttons, too many knobs, that if you move one, you might be breaking other. You have to have a certain order. All right, before we get into the matter, let's talk about Tableau and Redshift. It's just a fantastic combination. We have a lot of customers that are using it and are really happy with it. And it is an enterprise-class product integration. Let me show you what some of our customers and partners are saying. For example, Abhishek from Box, our customer and partner, talks about how easy it is to set it up, how fast it is, and how seamless the integration is. And that's just fantastic. Now, Jason from Pearson talks about from the angle of how the combination of those products allows you to forget all the mundane tasks and elevate your view at a strategic level, enabling you to foster and grow a culture of data in your organization, which is really what it's all about, and this is what Blueprint, for example, is about. So now, I'm going to ask you a favor. I'm going to show you two diagrams. Don't look at the details, just look at it as a whole. The first diagram is how Pearson implemented Redshift and Tableau a few years ago. Just look at it as a whole, and now I'm going to tell you how that same implementation looks in 2019, and you can see how it's growing. They were able to add more organizations to that platform, and it's, again, proven the enterprise level integration of Tableau and Redshift. All right, so now you're thinking, well, that sounds great. How do I make the most of it? How do I get that level of happiness with this integration? And that's fantastic. That's the right way to start, the right approach. Is almost like the check engine light on your car dashboard, where it tells you there's something you need to do. It just doesn't tell you what to do, and you don't know where to start, right? So we're going to do that. We're going to start with how do we map this problem? So remember the river metaphor, right? I'm probably going to just leave it at that. I'll let you make the analogies. But in our diagrams, queries flow from right to left. And then what we really care about, the data is collected on the left of the diagram and flows to the right, to the client applications. So in this case, we're looking at Redshift being accessed by a Tableau desktop, dashboards in Tableau desktop. And what you want to do is optimize Redshift first, and then optimize your dashboards. If your data source is slow, everything else downstream is going to be slow. But there's another situation where you might have a Tableau server in the picture. In that case, you want to optimize Redshift, but then you want to look at server and think about your processes and the usage that that your community is doing. Is it more, say, dashboard rendering heavy? Then you want more VSQL processes on your server. Or are you creating a lot of extracts? Then you want more backgrounders, right? Or you might be looking at a combination of VSQL during the day and backgrounders during the night. And then finally, optimize your dashboards. Or it can be a server cluster. In that case, optimize Redshift. Then look at your nodes. How many nodes do you need? How many nodes do you have? How are they configured, CPU, memory-wise, storage? Then look at the processes, not only what processes you're going to run, but also how they're going to be distributed among the nodes, because now we can do that with TSM. And then finally, look at your dashboards to optimize performance. Now, all of this can be the two situations, right, where you have users accessing dashboards through live connections, or you're creating extracts. Just to be clear, the extract line refers to the creation of the extracts, not accessing extracts from dashboards. That's independent from Redshift. But if you're creating extracts, then you're looking at Redshift, cluster, and server versus live connections from desktop would be the whole path. And then there are other factors that we have to just mention to fill the gap, which is infrastructure. Your network might be slow or congested. There was a couple of cases recently where customers were getting the impression that Redshift and Tableau were not performing, and it turned out to be the connection between their AWS environment, where Redshift and server were, and where the users were. Their pipe was just not enough bandwidth for it, and it was giving the impression of low performance. All right, so we're going to continue. One more thing is we're going to leave cluster optimizations, Tableau server cluster optimization and Tableau server optimization apart, because all those rules apply whether you're using Redshift or not. And I'm going to recommend a session at the end for server optimization. Now, we have a lot of content to cover, and we're doing good. Now, the one thing that I want to mention is that we're going to be concentrating on concepts. So when we look at the performance tips and recommendations, they just make sense to us. So I'm going to be spending a lot of time on the first 4 subjects. They're going to be the 4 legs of our table, and then we're going to put the surface of the table, and then everything else is going to be easy. All right? So now, I'm going to ask you a favor. If you see a slide with a diagram, that's a slide where we're going to have to understand the concept. Pay attention. Close Facebook, stop taking selfies. I'm talking to you guys. Yeah, I saw you. So let's see, when you see a diagram with slides with diagrams, pay attention. So let's start with a slide with a diagram. So that's a Redshift cluster. Remember the flow. Queries come from right to left, and then data flows from left to right. So the client application could be desktop, server, or any other. Talks to Redshift, this black box that we've heard about, over JDBC or ODBC. What happens inside is that there's a machine, an AWS instance called the leader node, that receives that query and then analyzes it, determines even if there's a better way to do that query. And then here's what's important. It attempts to distribute or slice the query into equal size jobs. So it can then send those jobs individually to each of the worker nodes that are behind it. So they work in parallel, and that's the concept that's key on this slide is they work in parallel on each one of those pieces, return the results to the leader node, it compiles it and returns it to the client application. So what we're looking for is parallelism. We get the most performance when we can do the most things in parallel. The worst case scenario is when, for reasons that we can discuss later, the query can only be satisfied by one node, and then you're wasting the rest of the nodes. But not only that, it might be that that node needs data that's sitting on different nodes, and that communication is a lot slower, so that's going to be less performant. We want to avoid that, all right? One more thing I want to mention is Spectrum. Spectrum is a Redshift feature that allows you to access through Redshift data that's sitting in S3. Now, in this diagram, I don't have Spectrum. Spectrum would be sitting where the storage cylinders, the white cylinders, are sitting, and it would be a software layer that makes it look like storage. And then when the request comes from the node, it would go to S3, get the data, and then present it as if it was coming from storage. As you can see, that's a completely different technology than local storage and requires a completely different approach for performance optimization. So because we only have so much time, we're going to leave Spectrum out of scope for this session, but I have included references in the deck that you can find for Spectrum to explore further. All right, so our first tip is a Redshift tip, and you'll see that I'll have Redshift tips followed by Tableau tips. They're usually related, and the Tableau tips are mostly about desktop or dashboard creation. So then on Redshift, there's two types of nodes based on their configuration. Dense compute and dense storage. Dense compute have a lot of CPU and memory and can do a lot of analytics really fast. Dense storage have more storage, so it's for when you need vast amounts of storage for your tables. Our recommendation is, if possible and when possible, is to use dense compute nodes. The next thing is that you can size your Redshift cluster based on your capacity. And you have two ways to do that. You can make each node more powerful, and that is scaling up, or you can have more nodes to achieve that parallelism that we were talking about. So our recommendation, obviously, is to scaling out, having more nodes, and that way you can achieve more efficient processing. And finally, if you're going to do that, if you're going to play with your cluster size, there's a feature called Elastic Resize that allows you to expand your cluster very easily in a matter of minutes and with very little interruption. So you can play with that. It's a lot easier than doing it manually. As far as Tableau tips, you're going to see a common theme, and that is You want Tableau to request the least amount of data back when it comes to queries. You want Redshift to do all of the aggregation, all of the calculations as possible, right? And then just return totals to Tableau. It's just inherently more efficient. There's less data coming down the pipe, and you're taking advantage of the vast amount of computing power that a Redshift cluster has. So you want to do that as opposed to, say, bringing it to your laptop and doing the calculations there. It's just, hopefully, sounds like common sense. All right. The next subject is distribution styles. Distribution styles is how you physically, or where you physically put your data in the Redshift cluster node. Distribution style optimization is about optimizing mainly join operations. There's also group by and create table as or CTAS operations that get optimized depending on your distribution style, but mainly we're optimizing joins here. The first distribution style is, and again, distribution is how the data or your tables sit on the nodes. So the first style is all, where the entire table sits on each one of the nodes. In other words, a copy of the table sits on each one of the nodes. The advantage of this is that the node has all of the information it needs to finish the jobs that are assigned by the leader node. It doesn't need that inter-node communication that's over a very fast network, but still network speeds don't compare to in-memory speeds. So it's a lot faster. Obviously, you're sacrificing storage, right? You're paying for more storage in order to get that performance. So it's up to you to decide whether an all distribution fits your environment and your specific tables. The next distribution then is spreading out a single table across nodes and based on the value of a certain column. So all values are going to be on one node and then all of the other values and so on. And that minimizes still, while it's not as minimizes as much as the old distribution, it still minimizes the need for nodes to talk to each other and share jobs. And finally, there's another distribution that's it's more for when you're not going to do joins with tables. That's the even distribution. And the point of this distribution is to facilitate the equal distribution of jobs between nodes. When you're not doing joins, you just go round robin, 1, 2, 3, and then back to 1 through 3. So the amount of data on each node is going to be about the same. There's the opposite of that is called data skew, where you have too much data on one node and then not enough data on another's, and then the load between the nodes is not evenly distributed. All right, so as far as tips go, you want to use auto distribution. And that means that Redshift is going to take care of deciding the distribution. At this point, it starts with a distribution of all, and then decides if it needs to switch to a distribution of even. Right now, it doesn't do key, but it's kind of logical to assume that at some point it will. So get in the habit of using auto distribution. If not, then I'm just going to flash you some of the recommendations as far as when you use what. All right, now let's look at how the data sits on disk. Let me start with something that's probably familiar with to most of us, and that is how a relational database is stored on disk. It's stored by rows or records, and when you need a value on a column, for example, Social Security number on our first column, you need to read the entire record from disk and then take just the value of the column you want. So if you want all of the values of Social Security, you need to read all of the rows to get that value. Essentially, you're reading the entire table to get just one column. The other style, and this is how Redshift works, is a columnar database where each column is stored on a separate file. It's a separate file on disk, and this is important to understand. There's quite a few consequences of doing it this way that allow the efficiency that Redshift achieves. So number one is, without getting too much into hardware, remember that when you read from a disk, regardless of which type of disk it is, you're reading by blocks. So in other words, if you need to read one character out of the disk, you still read the entire block out of the disk. So in the case of the columnar database, the more values or the most rows that you have of the same type of column, the more efficient it is, because when you read the one block, you're going to be reading multiple rows. Another level of performance you get is when those blocks are contiguous. And again, without getting into too much detail on hardware, both for rotational disks, the traditional disks that spin, or SSDs, the ones that are made by chips, it is still more performant to have the data in contiguous blocks for different reasons on each technology, but at the end it's the same conclusion. So you want your blocks to be contiguous. Another reason to have them contiguous is because Redshift uses something that's called a block map. And what it is, it keeps track of where data is. So if data is all contiguous, then it's a single jump. It's the block map starting over here and ends over here, one read, more efficient. If they're all over the place, then there's going to have to be more coming back and forth between the block map and where those blocks are. So conclusion is, we want our data to be in contiguous blocks. It's more performant. So when you go to design a table, you want two things. You want to use the less number of columns, because there's going to be less files on this to scan. And also, on those files, you want to define the columns as narrow as possible, because Redshift determines how many values it can fit on a disk block based on how you define the column, not the actual space that each value requires. All right? It's a fixed width. So the narrower you make your column, the more values it can fit on a single block, the less blocks it needs to read. And then as far as Tableau, again, common theme, let Redshift do the calculations. So another way that you can make that efficient is if you find yourself or your users doing aggregations very frequently, then you can save those aggregations on an aggregation table and just read that table instead of having to calculate every time. Last year's sales, as much as we want them to change, they're not going to change. It's the same number. Why have to go to the whole row? Just if you're looking at a monthly report, then just get the monthly totals, put it on a table, and save everybody some pain. All right. So let's talk about the way the data is arranged within the table. One thing about Redshift is that it doesn't use an index like we do on relational databases. It just sorts the data, and it keeps the data sorted. So how does it do it? Well, you designate a column or multiple columns on how to sort the data. So we're going to look at that. Remember, the thing to remember now is contiguous blocks, right? That's what we're looking for. So the first type of sort key is single column key, which is very simple. You just designate one column to sort the data, and everything's going to be sorted that way. Now, when you're looking for ranges on that column, it's going to be very efficient because it can find them really quick. Then do searches on the other columns, because then it's going to be, I'm going to get to that in the next sort key, which is compound. Compound is when you sort by more than one column. Redshift is going to sort by the first column, and then within each value on that column is going to sort by the second column, and so on. So it's going to be very efficient searching in that order. Just like we do at Tableau, right? We look at the data, and then we drill down, and then we drill down, and then we drill down. So if you drill down in the same order that the sort keys have, that's going to be super efficient, because Redshift is going to be able to find the values within that range. The other side of the coin is, if you do a search only on, say, the second column or the third column, then Redshift doesn't really know where things are. In this diagram, it's on purpose that product has a value of two values of A's on the north region versus the east region doesn't have any A's, to drive the point that if you search for just product and you want product A, you're going to have to search the entire table, and it's not going to be performant. So it's important for you to determine the sort keys and the order of your sort keys based on the queries that you're going to be receiving. Now, there's a third type, but we're not going to spend too much time on it for reasons I'll explain. It's the interleaved sort key. And what it is a compromise where you can't decide, for whatever reason, which column should be first, and you want to even out the performance. So you can designate multiple columns to be part of the interleaved sort key, and then the performance searching on each one of those columns individually is going to be the same between them. That's the good news. The bad news is that it's not going to be, any of those searches on each one of those columns is not going to be as performant as the single column or the first column on the compound key. So you're sacrificing a bit of maximum performance to kind of even it out. The other part of the interleaved sort key I'm going to leave you with, and then we're going to jump out, is that it requires a lot of resources. A lot of computational resources to add the data and figure out where to put it, and a lot of computational resources to find that data. Not only that, remember contiguous blocks? Well, we don't have that anymore. Look at that example. If you want product A, for example, you're going to have to find 2 blocks on the blue area and then 2 blocks on the orange area. If you want the north region, before it was contiguous, now you're looking at 2 blocks on the blue area and 2 blocks on the green area. So none of them are optimal. So interleaved is there, last resort kind of thing. All right, so tips. You want to use compound for dashboards for a reason I told you about, right? You want to be able to drill down and do that drilling of the data be very performant as you get more specific. If you're using timestamp, then you want to use also compound, because then it can find the ranges of dates that you're looking for. And finally, if you have quick filters, which are a fantastic feature, and they seem so little in the screen, there are some of these quick filters that in order to show you the values available, it has to do a scan on the table to find those values and then put them on the menu. So you're already doing a full scan of the table. If that full scan is based on a sort key column, then it's going to be faster. And then when you're joining tables frequently, the ideal scenario, and again, remember, it's up to you which one of those recommendations fit your scenario, but this is ideal. If you're joining tables, you want your sort keys to be the same as the distribution keys. In other words, the columns that you're sorting by are the same that you're distributing by. That way, the values of those 2 tables are going to be on the same node. And remember our principle, we want to make sure that a single node has all the information that it needs. So it's going to be more performant. Right? And then as far as Tableau, when you go to Tableau, you want to join tables on sort keys. And there's some rules about it. You can make some assumptions. If you know that all of the values on your table match each other, then you can enable Tableau to do more efficient queries. Filters, again, on the Tableau side, if you're going to do filters, try to do them on the columns that you're joining by. And definitely joining should not be on columns that have null values. It just creates queries in Tableau that are just less performant because they have to be more careful. Same for level of detail expressions. All right, so those are our 4 legs that I mentioned before. You want parallelism on the nodes. You want the data to have, each node to have all the data that it needs. You want the data to be sorted on the columns that are most frequently used. And you want your blocks to be contiguous. Those are our 4 legs. So now we're going to cruise through the rest of the subjects, because now everything is going to make sense. Let's start with compression. Compression is fantastic. I love compression. There were days back in I only read about it in the book. I wasn't born back then. But compression was very expensive computationally. Not anymore, right? The benefits you get from compression are so much, and the cost that you pay computationally is negligible. So you want to do compression. It's more performant because you read more data per disk block. Remember, we're reading disk blocks regardless, so the more data it's on each disk block is going to be faster. And it saves you storage. So you want to do that. You want to create the table with compression, and you want to do a copy operation because it compresses the data to on the fly. I talked about performance. I talked about cost. I'm kind of getting ahead of myself. That's a good thing. All right, now, the one thing that you should be careful is compressing on the column that you're using as a sort key. The reason why is because Redshift first looks on that column to see the rows that it needs to get on the rest of the table. So if it reads a block and that block has a lot of rows, then that's more scanning that Redshift needs to do on the rest of the table. So you want that column, it's like a book index, like a book table of contents. If you're looking for one page, but the table of contents only give you ranges of 100 pages, you're still going to have to search those 100 pages for that one page. So you don't want to do that. You want your sort key column to be uncompressed and then compress the rest of the table. All right? And I mentioned copy when loading data, so it gets compressed. And also, you want the compression to be, oh, that's right. So on temp tables or staging tables, you want to disable compression. And it's simply because they're temporary. You don't want to be spending computational power on compressing those if you're going to be removing them at the end of the operation. So just disable that. Now let's talk about encryption. Encryption is when you scramble the data so nobody can read it. The truth about encryption is that you either have to do it or not. You either have to be compliant or you don't. And if you don't, you usually don't do compression. So you don't have a lot of choices there. Now, the one thing that we recommend is that you get an understanding of the cost of that encryption. Because it takes computational power, and it's good for you to understand what that is. So when you're comparing, say, reading recommendations, you know how to translate that to what to expect from your system. So test your data with and without compression, just to understand what the cost of, did I say compression? I keep saying compression, right, instead of encryption, right? Yes? No? Nobody's stopping me? Really, guys? Come on, we got something going on here. All right, I meant encryption, yes. So you want to know how much performance you're paying for that encryption. Workload management is how Redshift manages the queries that come to it, right? And maybe receiving multiple queries from multiple clients. How do you handle that? How do you prioritize that? So that's workload management. Redshift can handle up to 50 concurrent queries. Now, it used to be a limit of 5, now it's 50. The default is still 5, but you just need to request it to be changed, and it's changed. And then you can distribute those 50 on up to 8 user queues. So in other words, you can designate queues that you can then set at different priorities. You can have up to 8, or you can just have one single queue that can handle the whole 50 concurrent queries. And it has, workload management can be set to auto, and I'm going to expand that. Let's talk about a concept that actually is the same concept that originated the cloud, and that is, if you have to plan for a peak demand, right, the top point on that blue line, you have to acquire capacity, you have to configure your cluster to handle the most the demand is going to get to. And in the meantime, when it's not at that point, you're just wasting that capacity. There's a feature called concurrency scaling where you can tell Redshift that when it receives read queries, it automatically spans additional Redshift clusters to handle that read query demand. And that way you minimize waste and you are still responsive to peaks on demand. So obviously, first recommendation is Enable auto workload management, enable concurrency scaling. There's also another feature called short query acceleration, and that is similar to the example I did with the extracts. And that is, if there's multiple queries, and Redshift does the analysis and realizes that there's one of these queries that's going to take longer, it lets the shorter queries to finish first, and then processes the long query. So you want to enable that. And then on the other side, you want to also enable or create query monitoring rules. And what that is a way for you to determine or tell Redshift to tell you which queries are not behaving. And that way you can take a closer look at that and optimize them or remove them or change them. As far as Tableau tips, same theme. You start your dashboards, the theme is request the least amount of data from Redshift. You start your dashboards with summaries. Your dashboard doesn't have to have all of the information in one screen. You can start with summaries and let the users click through. The perceived performance is going to be better. The user is going to think your dashboards are performing better just because for the summaries, you're going to need just a smaller number of queries than if you had everything. And as you drill down, you're only issuing the queries that you need. So it's going to be more performant. Keep them simple. And start with the smallest set of data on the filters. In other words, when we create a filter, we usually enable a default of all. And that means that there's going to be a query to get all of those values. Start with none or one value, and your query is going to be simpler, your dashboard is going to load faster, and then let the customer add values as they need. And also, provide an apply filter. What the apply filter does is it prevents from those highly interactive filters that are so cool that when you select a value, it immediately updates the data. But every time you select a value, it's an additional query. Let's just say that you don't really care about the first value or the second value by themselves. You just want the 4 values combined. Well, you're still doing 3 separate queries before the query that you care about. So you select the 4 values and then hit apply, single query. It's just good citizenship. All right, vacuum and analyze. The good news is that these two are becoming less and less relevant because Redshift has become more and more automated. When you add data to a table, and we're going back to how disks work, if you add a single row that goes in the middle of your table, it doesn't get physically inserted in the table. It initially gets appended to the file just because that's the way files work. And then later, Redshift looks at the data that's been appended, sorts that, and then does a rewrite of the table, inserting the rows where they go. But it's just the way storage works. You have to rewrite the entire table in order to get the new rows where they go. So that operation is called vacuum. And you can do it manually, but Redshift does it automatically for you. And it does it during off-peak times, so you really don't have to worry much about it. And then analyze is the gathering of the information that allows Redshift to do those calculations that I mentioned earlier to determine how long a query will take and if there's a better way to do this query. All of that information that it uses for those calculations, Analyze is the one that gathers that. Analyze also runs automatically on an hourly basis. Unless the system is too busy, then it pauses and waits until the system is available. All right, so as far as tips, again, they run automatically, but it may be that you add a lot of data and you want the data to be sorted right away. You can run vacuum manually. With stat update on, Analyze is going to be running every time you add data or do operations. And here's an interesting one. If you have a table that's sequential, let's say the sort key is a single column and it's a timestamp, and then you have separate files that are also sorted with that data. Well, append the files in the same order that they go. In other words, if you have Monday, Tuesday, and Wednesday, append them in that same order, and that way they're appended at the end, So the data is going to be sorted, and it's not going to require much vacuuming, right? If you do Wednesday, and then Monday, and then Tuesday, then data is out of sorts and unnecessary vacuum needed. Now, another feature that Redshift has is cursors. How many of you have heard that word? All right, I'm looking at you. It's your fault. All right. So cursors is a feature that allows you to issue a query that returns more data that you can actually handle. And what Redshift does is it uses cursors. It's just a term of giving you pieces of the data, as much data as you can handle at a time. But here's the key. Redshift has to materialize all of that data. Where does that happen? You want to take a guess? Yeah, the leader node. Even. All right. Yes, the leader node. So in this case, the leader node becomes a bottleneck, a performance bottleneck. And there are some situations where the leader node can run into errors because it runs out of space for the cursors. Depending on the instance type that you're using for your leader node, there's a set amount of resources for cursors. So you can run out of resources for cursors. And here's the bad news, is that it affects everybody. The whole cluster gets affected. So you do not want to run into cursor errors. Now, here's the key. And this is just my opinion. Don't condemn me for it. But the way I see it, it's not a limitation, and it's not a bug. It's actually a symptom. It's a symptom that we need to optimize our queries. If you're issuing a query that's returning so much data, you're not summarizing, you're not aggregating, you're not simplifying. You're just asking for too much data. So that's my personal recommendation when you look at cursor errors. All right, I talked about limits and impact. So one thing you can do, but again, it's kind of patching the problem, you can increase the number of concurrent cursors that you have. It's just a setting, and you can temporarily allow for more operations, cursor operations, handled by the Redshift cluster. You can do that on Redshift. You can do that also on Tableau. We support that, and you can do it at a data source level, or you can even do it at a workbook level. So again, it's a temporary fix. It's really a symptom, but in the meantime, you can kind of handle it that way. Aggregate, aggregate, aggregate. That's how you avoid cursor errors, right? Another way to avoid cursor errors is with your extract creation. You don't want too many extracts to be running at the same time, because you may then run into that limit, and it may be that it's just a matter of scheduling the extracts in a different way to avoid that, running into that limit. Now, I have a series of points about extracts here, just because they become practical, but this is not Redshift specific. This is just good extract citizenship. So you want to check the size of the extract, again, to avoid running out of space on the leader node, because if you run into cursor errors, you affect other users. And if you do, then one solution is to scale up your leader nodes, because the cursor resources are fixed per instance type. So if you want more cursor resources, you need to change the instance type of your nodes. All right. So consider the entire data journey. Look at it as a river. Start from Redshift and work your way through server or server cluster to your dashboards and finally your users. You start with Redshift, knowing the kind of queries that it's going to be receiving. So optimize Redshift based on what customers are going to be issuing. And then, of course, simplify your dashboards. That's a loaded term. you want to aggregate your measures, you want to reduce the number of measures that you display at a time, you want to simplify your filters, use the apply, and all of those tips. Now, if you want to know more, we just updated a white paper on Redshift and Tableau. So you can actually scan it if you want, but you have this deck. It goes a little bit more in detail on the things that I've mentioned. And there's also a couple of sessions that I want to point you to. One is about Tableau performance optimization, and also about Tableau server. As I mentioned, I didn't talk about Tableau server optimization because there's plenty of material out there. Now, I'm going to flash you through 4 slides. Don't panic. I just want you to see that I wasn't lying when I said I got plenty of references for you when you look at this deck. And finally, I want to ask you to take a minute, and here's why. This is very important. This year is the first time that we have sessions specifically about the public cloud. We have a session track about public cloud. We want to know what you want out of this type of session. Tell us if the level of material is adequate. Tell us about subjects you want to hear in this type of sessions, because we're looking for that feedback, right? Not only talk about how wonderful the presenter was, I know that. Okay, no, I'm just kidding. Just really tell us the feedback. Now, we have a special guest. We have our friend Srinivas from AWS. He's a partner product consultant in analytics and data. He's going to serve not only as our microphone man for questions, but also he's going to respond to questions because he's the expert, actually. I learned everything I know from Srinivas. So, anybody has any questions? All right, we got one here.